All right. Welcome, everyone. This is Robin speaking. We are here gathered at the philosophy department in person. Today, we have the great pleasure of having Michele Caprio joining us from Duke University. Michele is a graduating student from the statistics department, and he will soon be joining UPenn for his postdoc. And today, Michele is here to share with us his work with his advisor, Cheyenne Mortgagee, on extended probabilities and their application to statistical inference. Welcome.
Thank you very much. So, first of all, thank you very much to Robin and Snow for inviting me, and to everybody who's attending. This is a very open paper, so I very look forward to difficult questions and criticisms. Right. So. Okay, so the main goal of today's talk is to give a general definition of extended probability measures, what we mean by that, study some of their properties, and provide a behavioral interpretation. And then we want to use them in an inference procedure. In an inference procedure, the environment is canonically represented by the probability space omega fp, and we will use extended probabilities to take into account when both p and the composition of omega are known. We end up with an ex-ante analysis in which we progressively learn the true composition of omega, and this allows us to form an initial p. We also give a toy example in the field of ecology. So extended probabilities I put quote unquote because they've been used in various literatures having very different meanings. They are in general set functions defined on the sigma algebra F, whose codomain is either a superset of 0, 1, or is defined using entirely different number types, for example, p-adic numbers. They first came up in physics, and then they became popular in other fields like economics, machine learning, stochastic processes, queuing theory, and of course mathematics. And here are some references if you're interested. So the first question to answer is why studying extended probabilities. So as I said before, extended probabilities have been given differing definitions and interpretation both across and even within fields of study. So what we wanted to do is to give a foundational or basic definition of extended probabilities. And we came up with two properties that a set function must have in order to be called an extended probability, irrespective of the environment the scholar works in. And we tried to give a behavioral interpretation. And then the following question is, why would you want to use probabilities that can go negative in statistical inference? Right, so we are considering the case where the state space is at most countable. And we, of course, went at it with the power set, the sigma that is a power set. And the space usually adopted to express uncertainty around the elements of F is the probability space omega fp. Now, to express further uncertainty regarding either the composition of omega or which p to consider on omega f, we can use lower probabilities. For example, Robin in her 2018 seminar had to use lower probabilities as a consequence of survey non-response, where she was forced to consider an enlargement of the original state space to a power set. And in that situation, probabilities could not be computed exactly. So only lower and upper bounds were available. And therefore, lower probabilities were used to capture uncertainty around omega. Instead, in the second case, that is, if we want to express uncertainty on which p to consider on the measurable space omega f, we can use the triple omega f calligraphic p, where this is a set of probabilities, and this would we would proceed as in my paper with Robin and another one with my advisor, where p then is updated using some procedure. In our case, it's based on Jeffrey's rule, but basically the idea is that we express the.
I was trying to kill something that was very annoying, and now I've lost the window. How do I do that? I'm so sorry. Hold on a second.
Yeah, no worries.
back to meeting. Maybe that.
Nice. No worries.
Sorry for the interruption.
So yeah, so to the best of our knowledge, there was no cogent way of expressing uncertainty on both the composition of omega and which p to consider on omega f. And we tried to fill this gap using extended probabilities. And then we also give a simple example for species sample problem. Right, now the technical definition that we gave to extended probabilities is this one. So we have a measurable space omega f, and an extended probability is defined on the sigma algebra f. So it's a functional on a set functional on f, for which the extended probability of A is between -1 and 1, and we require it to be countably additive. So as you can see, an extended probability is a finite sign measure, and condition 1 star and 2 star are more general than the axioms of Kolmogorov because we don't require the probability of omega to be 1. Okay, so before I go on, any questions on this?
There's one. So do we also require that somehow the whole space sum up to 1?
No. The probability of omega can be smaller than 1.
Can be smaller one, but not greater than
Not
1?
greater than 1.
And can it be less than 0?
Yes.
So the whole space can sum up to something between 0,
Between
-1.
maybe 1 is 1 and 1.
Oh, I see. Because you're saying that for all A, so
Yes.
that A could include the whole set, and also you have counter
Yes.
additivity.
Yes.
Got it. Thanks.
Of course. Right. So we also tried to give a behavioral interpretation to framework extended probabilities within a subjective paradigm. Hopefully, I can convince you that this is interesting. So if the probability is positive, then we give the usual definite interpretation. So if we can enter a bet about event A that gives $1 if event A happens and 0 if it doesn't, then the probability we attach to A is the number small p, that is the amount of money we deem reasonable to pay to enter the bet. Now, if we are not given the possibility to enter a bet, like the aforementioned one, we cannot assess a probability for A as before. And the idea here is that maybe this A is a latent bet. Such a possibility, though, is given to our doppelganger, so a fictional character that is basically the copycat of us. And they tell us that their subjective yes?
Johannes. I would have just a question about the slide from before. Sorry
Yes.
for interrupting.
No.
So you have this sum, right, which sums up to the probability of the union. So the probability of the unions is equal to the sum of the probabilities. This was the second condition in the definition of extended.
Yes.
Maybe it's even one more slide before.
This one?
Yes. So
Okay.
I'm wondering about, it's a mathematical question. I'm wondering about the sum. So you're summing up positive and negative numbers here, right?
Yes.
Does it matter in which order you arrange the sum?
No.
So this is just a condition on the probabilities that however you arrange the A's, you get exactly this. Okay.
Yes.
Okay, fair enough. Thanks.
Sure.
Or maybe, can I just quickly
Yes.
follow up? So are you just assuming that it's supposed to converge? The sum is supposed to converge?
Well, the condition would imply that the sum of all the positive ones is less than 1, and the sum of all the negative ones is bigger than -1. That would be a consequence of condition 2. So you'd have this absolute
Absolute convergence.
convergence.
So you can't have a possibility of 1 over n plus minus 1 over n plus 1 over n. I see. Got it.
So okay. So back to the interpretation. If we are not given the possibility to enter this bet, we assume that such a possibility is given to a copycat of ourselves, which we call the doppelganger. And they tell us that their subjective assessment for probability A is some Q in 0, 1, so their subjective probability. And we assume that the doppelganger assigns the same probabilities as ourselves to all the events that we can both enter a bet about. Now, if we were given the opportunity to enter the bet about A, the amount of money we would deem reasonable to pay would be Q dollars. And so we are prepared to lose Q dollars in the case the complementary happens. And therefore, we set P equals to minus Q. So basically, we are flipping the sign to the probability that the doppelganger assigns to the event A that we cannot enter the bet about. Yes, so this is the interpretation we try to give to probabilities that can go negative. And we say that if later on we are given the opportunity to enter a bet on event A for which we were not given the opportunity before, we are not required that the probability that we assess is equal to the absolute value of the one we gave when we weren't given the opportunity. If indeed it's the amount is different, this means that we change the idea about how likely event A is once we are given the possibility of entering the bet. Instead, if the probability is actually equal to the absolute value, we are obeying to what Allen called the principle of conservation of knowledge. Here, knowledge is defined in a very heuristic way, which means that information is not created nor destroyed, but just transformed. So the total amount of knowledge is constant. And when we go from something that we couldn't enter a bet about before, and then we are given the possibility, then the probability is an absolute value. Yes.
I have a
Go ahead.
So I have a question about this, because I guess on the previous page, because you were talking about the interpretation where if we have a negative probability of an event, that would mean that we cannot enter a bet about that.
Mhm.
So it is possible that I could bet on an event that is a superset of A, as well as a subset of A, for which the probability assigned is.
Yes, we have an example on the paper where you have like the probability of a thunderstorm, and you can enter a bet on rain, but you cannot enter a bet on dry thunderstorm. So a thunderstorm without rain. So there can be events for which, for a sub-event, you cannot enter a bet.
I see. So it's basically like you have these collections of events that have a zero or positive probability attached, and there are these that are negative, and those are the ones. It could be that they have logical relationships.
Yes.
But it's just that it's purely like the value of the probability attached to
Yes.
this. Okay.
Do I understand correctly? The doppelganger doesn't, his probabilities, he's got all the same positive probabilities as you do,
Mhm.
but then he has other positive probabilities too.
Yes.
So his probabilities may add up to more than one. Is that correct?
His probabilities will yes, maybe this is the thing that we were missing towards the quantum interpretation. But yeah, I think maybe then I should say that we renormalize everything. Yeah. So that it becomes feasible. This thing of asking their opinion.
So basically, the probability assignment by the doppelganger, there is no law that governs.
Yeah,
it.
exactly.
That probably does not have to obey
Yeah, exactly.
1 star and 2 star.
Exactly.
Okay.
Can I
Yes,
also ask you?
sure.
But good
That's
thing
what
to-
we do.
No,
Anyway.
No, of course,
Yeah.
of course.
Can you just say a little bit more about what you mean by cannot enter a bet?
Yes. So what we had in mind was events. So for example, suppose okay, I have a background in economics. So sometimes you want to measure, say, the quality of living. And the quality of living maybe depends on something like happiness, something like that. And happiness is somehow very difficult to observe, it remains very latent. And so there exists, for example, the event that happiness exceeds a certain threshold, right? But you cannot observe that event. And our idea was to assign to those events probability that is negative. And if you end up after a while being able to observe those events, then you could flip the sign to positive or reassign completely. Or if if it remains unknown forever, it remains with a negative probability. But one shortcoming of our of this technique that we will develop in the statistical inference paradigm is that we require that the state space ends up being discovered. So we still haven't developed something that can actually take into account these latent events, remaining latent forever.
Thank you.
So
There's
yes.
a question by DTL.
Yes.
Can you go back to the to this countable additivity statement on that
Which
Johannes asked? The same one that Johannes asked a question about, like the countable.
This one?
Yeah, this one. Yep, that's right. So if I'm right, this your doppelganger also assigns probabilities, but only positive probabilities, and you would like to interpret the negative ones as being basically your doppelganger's positive probabilities, except that you are not allowed to bet on those events.
Yes.
Now, is it not the case that let's call your doppelganger's probability assignments as Q, just for simplicity, meaning so Q is on 0, 1, and basically, it's the absolute value of Px is Q, and that's what your doppelganger is using. That's not a probability distribution, right? Like that will not obey this countable additivity. That is, Q of the union will not be the sum of the Q of A.
Yes. That's what Glenn was saying before. Yes, I think here I either need to adjust the definition or justify why this can happen.
No, I think Glenn's question was about the total Q of omega being potentially larger than 1, and you talked about normalizing that. I'm talking about even other subsets that don't have their union as omega. Now this countable additivity wouldn't hold because earlier, I guess there's.
No, I see what you mean. Yeah, it's basically what happens then is that the probability for the doppelganger would be just a sign measure, a positive sign measure, right?
Right, I see. So your doppelganger doesn't itself have a probability distribution.
I think, I
Okay.
think so. Or I need, again, I will need to think more about this. So thank you very much.
Okay, thank you.
All right, I talked about this. I think so. Yes. So yes. So we found some properties of extended probabilities. Here I only present some of the more pertinent ones, but I have more if you're interested in the extra slides. So we call the triple omega FPX an extended probability space. And because we do not require the extended probability of omega to be 1, the extended probability of the complement of an event is given by the difference between the extended probability assigned to omega and the extended probability of A. And this equation here ensures us that the extended probability of the empty set is indeed 0. And also we have that by countable additivity, the extended probability of omega can be written as the sum of the extended probabilities of the elements of a partition. Also, we have that extended conditional probabilities are just the extended counterpart of regular conditional probabilities. So they are defined as the extended probabilities of the intersection over the extended probability of the conditioning set. And to avoid confusion arising from the sign, we say that A and B are independent if this condition happens. So the absolute value of the extended probability of the intersection is equal to the absolute value of the product of the extended probabilities. And this was already introduced by Alan. We just thought that that may be interesting to carry over.
So
Yes.
Alan did these negative probabilities or something.
He was one of the first ones who started. Yes.
Sorry, quick question, which is independent of my previous one. On the previous slide, you had this partition. So is this independent of the partition that you use? Is that obvious? Maybe it is obvious and I just didn't get that.
Yes, here I'm saying take any partition, then the probability, the extended probability of omega is just the sum. It comes from the countable additivity thing. This is not even even interesting, I just put it there because I'm going to use a partition later.
Okay, thanks. And so you're saying it is independent, no matter which partition you choose.
Yes.
Yeah, okay.
Yes, it's like, yeah.
Oh, I see. So this is related to the thing that it does converge because both the negative and the positive subsequences sum to 1. Okay,
Yes.
thanks.
Anything else? Okay. So because we wanted to frame these extended probabilities in the subjective paradigm, we thought of introducing the concept of a Dutch book. So if we have a generic extended probability space and we consider the sigma algebra of the events that we can enter a bet about, a Dutch book is a finite collection of these events along with real numbers such that this inequality holds. And this is basically telling us that the SJs are the payout for a winning bet on BJ, and SJ times PX of BJ is the bets fair by E. And this is basically the usual definition. And the inequality suggests that we can build a bet such that the bookmaker always makes a profit and the punter always loses money. And we say that an extended probability is coherent if no Dutch books can be made against the punter. And it turns out that the extended probabilities are always coherent because they are countably additive. So the proof techniques goes along the way of the one proved by definitive. And in our definition, we do not take into account the events for which the probabilities are negative, because those are events for which the punter cannot enter a bet. And so they cannot just be used to build the Dutch book.
Sorry, can you go back to the previous slide? Just quickly. Sigma. Oh, it's general. Do we know the set of B such that you have non-negative probability, extended probability B? That may not itself be a sigma algebra. But
Yes, the one induced by.
Induced by, which might,
yeah.
which might include events not in F originally.
Yes.
Can it?
Oh no, sorry.
not in F.
It will be a
That-
sub-sigma algebra.
Yes.
What is the point of defining this sigma algebra? Oh, I see.
Those are the only ones on which you can bet.
Did we know that? Okay. No. If you take all the ones that have positive probabilities and form a sigma algebra generated by them, not everything in that sigma algebra will have positive probabilities.
Why not?
So suppose
Because your sigma algebra has complements in it.
Right. So
well, but if so everything in this sigma algebra would belong to the bigger one.
No, I'm not worried about it not being in the bigger one. I'm worried about having a negative probability.
Right. But isn't it by definition that this one is constructed with only collecting those that are positive?
And their complements.
So this set itself would not be a sigma algebra. So when we think about the sigma algebra generated by this set, it would include like complements, which would not be events that you assign non-negative.
Because previously you did, because you only required countable additivity. You didn't say that a smaller set could not take a probability as larger than a larger set. So it's possible that a smaller set has a probability.
No, I'm not talking about smaller sets, people. I'm talking.
Yeah, I mean.
The sigma algebra includes complements, doesn't it?
Yeah.
So the set of everything. Omega is a countable set. So the union of everything with a negative probability has a negative probability. And it's going to be in that sigma algebra. The union of everything with a non-negative probability is in the sigma algebra. So its complement is the union of everything that has a
you're right. So
has a negative probability. It's in the sigma algebra. So that sigma, you don't want that sigma algebra.
exactly, it should be just the collection, right?
Yeah.
The collection. My bad.
Well, but if you have just a collection, what does this say? I thought that when we do the Dutch book, it's like the bookie lays out all these bets, and I could choose to bet on either side.
Okay, so you want a sigma algebra of a smaller.
So I guess since since equation 3 allows Sj to be reals, and you can bet on either side, maybe we should just generate the sigma algebra from the collection B such that Px of B is greater than 0 and Px of B complement is also greater than 0. Like you were allowed to bet on both B and
Oh,
B
I see.
complement, and you generate the sigma algebra from that. Then it might fix the issue.
And then you would have it by definition, but then you are also left with a smaller collection of events compared to
Yeah.
how you started with. I see.
Thank you.
Yep.
Thank you. Thank you. And then this one also. Now, I want to use extended probabilities in statistics because as I told you before, I want to consider the case in which omega is not known at the beginning of the analysis, and p is not known either. We cannot select just one. So we build an ex-ante analysis in which we progressively learn the true composition of the state space. We assume that omega is almost countable. So this is another shortcoming of this way of proceeding, that for now it's only developed for omega at most countable. And at time t, we assume that omega can be divided. So I use the square cap here to denote disjoint union. Can be divided into a latent part and an actual part. So the latent part will be the part that we don't know at time t, and the actual part is the part that we do know at time t. And at time t0, we assume that portion omega 0 plus is known ex ante and is assumed non-negative. So this, for example, may come from previous experiments that are similar but not equal to the ones we are considering, or any other way of having an initial opinion about a subset of this big domain. So the most general way of proceeding would be to specify the number type we believe we're working with, so natural, wholes, integers, or rationals, and setting it to be omega, and thus giving the omega the apparently possible interpretation of all this. So here it need not be the whole number type, sorry. It just has to be the omega that contains all the states that we believe are logically consistent with our available information. So for example, an apparently possible state space, the apparently possible state space associated with a coin toss would be one having inside heads, tails, coin landing on its edge, coin breaking into pieces on landing, coin disappearing, Stella cracking, or something like this. And given the two sequences of apparent and latent spaces, we require that the sequence of apparent space is monotonically non-decreasing, and the one of latent spaces is monotonically non-decreasing, so that we can say that the limit of the former is the union of all the apparent spaces, while the limit of the latter is given by the intersection of all the latent spaces. And this leads us to two possible scenarios. One in which we have that the union is the whole apparently possible state space, which implies that the intersection is empty. And the other one where the union is a proper subset, and therefore the intersection is empty. So what we do is at time t0, we specify the finest possible partition of omega that we denote by calligraphic E. And E is such that this is true, and here I'm abusing notation, but here I mean that E0 minus is the finest possible partition of omega 0 minus, and likewise for E0 plus. Now, at time t plus 1, when an element, say omega tilde, is observed that used to belong to the latent space at time t, then the element of the partition of the latent space at time t becomes an element of the partition of the actual space at time t plus 1. and we write this equality right here. I know the notation is a little baroque, but I think it's kind of self-explanatory, hopefully. So we have that for all t, again, abusing notation, the partition of the latent space, the actual space at time t+1 has at least the same amount of elements as the one at time t, while the partition at time t+1 of the latent space has at most the number of elements that it used to have at time t. Does this make sense? All right. So in the first scenario, that is when in the limit we discovered that the sample space associated with our experiment corresponds to the whole set of apparently possible states. In the limit, we have that the partition Et plus coincides with the partition of the whole set omega, and Et minus, the limit of Et minus is going to be the empty set. While in scenario 2, omega prime can be finite or countable. If it's finite, this means that there exists a capital T, so a moment in time, after which the observation we collect at time t plus I already belongs to omega t plus for every I. So omega prime is actually omega t plus. So we discovered that the actual sample space associated with our experiment is finite and smaller than the space of apparently possible states. If instead omega prime is countable, we can only say that it is a proper subset of omega, and we discover it's in the limit. Now, this is another interpretation that I hope you like. So our ex-ante analysis is concluded by finding the true composition of the state space, and we interpret this as the existence of a benevolent bookmaker. And with this, I mean the following. So while our doppelganger is always able to enter a bet on all A in F, we end up only being able to bet on events that are crucial to the statistical analysis. So this corresponds to a benevolent bookmaker that prevents us from entering bets on irrelevant events that, if we were given the opportunity to bet on, would make us lose money. With this, I mean that suppose that there is that we discovered that our sample space is actually this omega t plus, right? And so there is some set in omega t minus, and suppose we were given the possibility to enter that bet, and we deem it plausible, so we don't assign that negative probability, zero probability, then we would certainly lose money on that, because that event would never happen, because it doesn't belong to the state space associated with our experiment. Instead, there are cases in which the state space does not get fully discovered. This is a very silly example, but like think of an urn with a timer attached, that once the timer runs out, seals the urn, and so that we do not discover its entire composition. This case would correspond to the existence of a malevolent bookmaker, which does not allow us to enter bets crucial to the statistical analysis, because we do not end up discovering the full composition of the state space. And so this would give us the opportunity to study latent events. Yes?
So I guess the benevolence is only true if you're allowed to make one-sided bets, is that right? But when you were Dutch booking, you were allowed to make both-sided. That means you can buy or sell from the bookmaker. And so, in fact, you could make money if you sold it to the bookmaker. The bookmaker, isn't that right?
Yeah, I think you're right, yes. So it's just one-way bets, right?
Right. So, I mean, I guess the bookmaker is not that benevolent, because if they really allowed you to bet both sides, you can make money against by betting on.
Okay. So let me call it almost benevolent then.
This actually reminds me, so if you have this distinction, right, why do we then need coherence the way that you were trying to formulate it? Because unless we hit eventually the wonderful scenario in which we actually discover the entire space, then you wouldn't be you would be prevented from betting on things that would nevertheless be positive.
Because in that case, because that is the more general case. So here I'm doing all these further stricter assumptions because I wanted to apply to statistics. that was just a
So you
general
were saying that would be
definition.
the ideal
Yeah, yeah.
scenario, like.
That is just a general the general definition of coherence.
Okay, okay. Can you explain again, so why is it that if we don't get to discover the true composition, so we're missing out on a portion of it, why would you call that a bit malevolent?
Because so when I wrote this, I was thinking of, so you're not given the possibility to enter bets on events that you would want to bet on because they are crucial to the analysis.
But this would not really impact my coherence per se, right? Because the fact that I don't get to bet on something doesn't mean that I will lose money for sure. So the benevolence or the malevolence comes from restricting my menu,
Yes,
not so much
exactly.
trying
I
to
think so. Yes.
take advantage.
Sorry. Okay, so all right. So before discussing an operational way of attaching extended probabilities to the elements of the sigma algebra, I want to discuss an interpretation that we gave to the extended probabilities attached to omega. So because of the way we describe things so far, omega can have extended probability 0, negative or positive, but not 1. So if the extended probability of omega is 0, that means that we have no sufficient information to say whether the sample space associated with our experiment is in fact omega at time t, the information at time t. If it's negative, it means that for the time being, the sample space associated with our experiment appears to be a proper subset of the bigger omega. And if the extended probability is positive, but not 1, then it means that for the time being, there is a convincing evidence that the sample space could be omega, but we cannot state with certainty yet. So this is very...
So is the word convincing like the same as the word sum here?
Is the word also?
Well, why do you say convincing?
For the time being, we are missing. We still want to observe more elements to be sure that the state space is the one given the apparently possible interpretation. Yes.
Well, I think I don't understand what's going on.
So I guess maybe I'll ask my question about this physics axis. When you say convincing, usually when, in regular kind of probability, when we say convincing, it basically means the probability is pretty much 1.
Yeah, no, here I mean, that, okay, that means that for the time being, we have a probability that is kind of approaching to 1 in a sense. So because we have seen the actual space expanding and expanding, we think, oh, maybe the state space associated with the experiment is indeed the bigger one. But we cannot say it with certainty at time t because we are still observing elements. Does that make sense? So if I understand you right, then I would state the two latter point to be like, if that is negative, then it's convincing evidence that we're not there yet. Right.
Whereas if it's positive, then we may be getting there, but it's still. I mean, what would be actually, because you kind of want to have a measure of how convincing it is that we have approached pretty much the end of. I mean, because there's another thing, right? Because there's no guarantee that as we expand the space, the total probability assigned to that would actually always go up. So you could actually go up and then down and then up, right? So as the omega plus gets larger and larger, the total PEX assigned to it can go up and then down and then up.
Why can it go down?
Why can it go down? Oh, maybe it cannot go down. Can it go down?
I don't. think so, right? Because it's expanding, so it's
It's expanding. Oh, because you're always flipping the negative ones to positive. So that always goes up. But you don't also expect that to go all the way to 1 either.
okay.
Is that right? That's my question.
It can go to 1 if omega t plus converges to big omega, if the union is big omega.
So when it does hit 1, you know that this is it.
Yes.
This is my space.
Yes.
But before you, okay.
And it can also happen that again it's smaller, and therefore this will never have probability.
Okay.
Okay, so thank you very much for the. Again, this is just heuristic. There was nothing mathematical behind convincing, but thank you very much for that.
Can I ask you one?
Sure, of course.
I'm so sorry. So far, are you just ruling out the possibility that the omega is a subset of some bigger truth space?
This omega right here.
Yeah, the omega right here.
Yeah. Here it's the biggest you
The
can.
biggest you can
Yeah.
possibly get. So it's only there's no possibility that you can.
Yes.
It's actually a subspace.
Yes. So this is. I'll save this comment for later. But
Okay. Yeah.
Okay, so this is a way to operationalize the assigning extended probabilities to events. So if we consider any probability measure, a regular probability measure P on omega f, and this probability measure is such that for every element in the sigma algebra, for every event A tilde in the sigma algebra, P of A tilde is some small p, that is the amount we infer to A to enter a beta about A. Then what we do is that we say that the induced extended probability of the portion of A that lives in the actual space is exactly equal to P, and the portion of A, the extended probability of the portion of A that lives in the latent space has a flipped sign. Then we have that Px0 satisfies 1 star and 2 star, and it's a properly defined extended probability measure. So this, of course, looks like cheating, right? But it's at least from the doppelganger point of view, it's what would happen if we were to assess the probability of events that belong to the actual space, and then we ask our doppelganger for their probabilities for the elements on the latent space and flip the sign to those. Okay, so here it's P0 because it's the initial one, D for the doppelganger. I think here it relates to what we were telling about before, the finite sign measure for the doppelganger. Sorry. So to update extended probabilities, what we do basically is we require the principle of conservation of knowledge by Allen to hold, right? And this is all notation that I will walk you through, but basically it's what is going to happen. So suppose we collect a new observation, and if this new observation used to belong to the latent space at time 0, this means that at time t1 we learn a new element of the true sample space. So the element is the element of partition E0 minus consistent with omega at time t1 becomes an element of the partition of the updated actual space, and in formula we write this. So again, this abuse of notation, as I told you before, and basically the updating probability works exactly like this. So we assign to the element that used to belong to the latent space, now to the actual space, we flip the sign to the probability it used to have when it was in the latent space. And instead, the extended probabilities assigned to the other elements are held constant. If instead, at time t0, if at time t1 we observe an omega that already belongs to omega 0 plus, then we don't do anything, we don't update it. So because we're working with the finest possible partition of omega, the updated extended probability can be written as this monstrosity right here, and now I'll walk you through the sums. So it's basically, I'm telling you, consider the extended probability of assigned to A is given by the sum over the elements of the updated partition of the actual space. So this is the partition of omega 1 plus, such that they intersecate event A, and they themselves have non-zero extended probability, plus same thing, but with the elements in the updated partition of the latent space omega t minus. And as I told you before, we are implicitly assuming Allen's principle of knowledge to hold because of that, because of this way of proceeding. And this has a practical advantage, two practical advantages actually. One is to update that the updating procedure is mechanical, and this one that we preserve the initial opinion of the researcher. Now, of course, I know that this sounds very counterintuitive, but bear with me. I have a couple of slides on this. Okay. Any questions? Yes.
Clarification. Do we know that this one is still bounded by between -1 and 1? Because you have already flipped the negative sign to positive?
Yes.
But we still.
Yes, because of the way we chose here. Because the way we chose here the negative portion. Because these come all from a regular probability. So we're sure that they would not ever go above 1.
Because I feel like you are preserving all the probabilities of the partitions compatible with A, but also adding a probability from which was negative before and then adding.
Yes. But again, all the extended probabilities at the beginning come from a regular probability. So they will never, even if we take the absolute value of everything, they will never go above 1. Like they will be equal to this, which is a regular probability.
So does that mean that I could understand? I mean, it's almost like a backwards kind of way to say that we had a countably additive not regular, just ordinary probability to start with, and let's try to flip those sets to negative because those things we cannot.
Yes, and then if it tends, this is spoiler alert, if it ends up that if it ends up that capital omega is the real state space associated with our experiment, we retrieve this very P. If instead is a smaller one, we have a projection, again heuristically, not really, but a projection of this P onto a smaller space.
But wouldn't that mean that you needed more than I star and 1 star and 2 star to begin with as sort of?
No, but in this case we are doing this trick, but in a more general case, it doesn't. If I ask the doppelganger to have just a finite sign measure instead of a probability, yes.
So not every extended probability satisfies these two equations, but you're just looking.
Yeah, exactly.
Oh, I see. Okay.
I think
Well, but I guess the question is that if I have a extended probability that satisfies 1 star and 2 star.
Yes.
Is it guaranteed?
No.
So it's not guaranteed that
No.
we will, if we do this, we would again.
Yes.
So which one is the chicken? Which one is the egg? Do we get the P first or PX first?
First we get P. So this is a fictional, this is a fictional way of so the doppelganger doesn't exist, right? So what we are doing is saying, okay, I imagine that I know the state space that is the biggest possible.
Mm-hmm.
If that were the actual the real state space associated with our experiment, my subjective opinion would be captured by this probability. Then I consider a subspace of the sample space, which I call omega 0 plus, and for everything that lives there, I keep the same probabilities. For everything that lives not there, I flip the sign.
Mm-hmm.
And as I know more and more the composition of the state space, so as more and more this omega 0 plus increases, I flip the sign. I revert the sign to the probabilities that I keep, of the elements that I keep discovering.
I see.
Does that make sense?
I think it does. It does. I guess because you have taken an oracle view. That would be like, if you knew everything, that's what happens and unfolds.
Yes.
There's this question of, if I were somebody who didn't know what was everything, how would that lay out for me if I didn't know what was P to begin with?
No.
Because that was the question.
Later I generalized this to set of probabilities in that time.
But I mean, I understand what you're saying with this mechanical illustration.
I'm
That-
happy about that. And if there are no more questions, I'll go ahead. Okay, where was I? Here? Yes. So as I told you before, like if instead we observe an element that was already in the actual space, everything stays the same. Now, if we call Px infinity an extended probability that is defined as this, so the extended probabilities of the portion of A that lives in the union of all the actual spaces is equal to the probability that we used at the beginning, as Robin called it, the oracle probability of the same event, and the Px infinity of the portion of A that lives in the intersection of the latent spaces is equal to minus the oracle probability of the same event, right? So we have that if we call Pxt the sequence of updates of our Px0, and DETV the extended total variation distance, which is the total variation distance between extended probabilities that is exactly the same as the usual one. We have that as t goes to infinity, Pxt converges to Px infinity in the extended total variation metric. And if this holds, so if we are in scenario 1, where we discovered that the sample space associated with our experiment is the whole apparently possible state space, then the extended probability assigned Px infinity of omega is 1, and so Px infinity is just a regular probability measure. So again, this is exactly the oracle way of proceeding that we were saying before. So now, any questions? So far, we used extended probabilities to capture the uncertainty on the composition of the state space, of the sample space. Now we want to capture also the inability of the agent to specify a unique extended probability measure on omega. And to do this, we work with sets of extended probability measures. This corresponds to having an extended sensitivity analysis approach that is the extended counterpart of Bayesian sensitivity analysis introduced by Berger. And this means that we begin by considering a set of extended probabilities that represents the agent's initial beliefs, and we will have a sequence of successive updates of these initial beliefs. This represents the condition of a researcher that faces a decision under ambiguity, because maybe the information is scarce, incomplete, something like that. So how do we update the sets of extended probabilities? Again, very, very intuitively. So if we call calligraphic Px infinity the set of element-wise limits in the extended total variation metric of Pxt for some Pxt in a set in this sequence, then we have that the sequence of successive updates Pxt converges in the Hausdorff metric to this Px infinity, because we have because of the way we define this calligraphic Px infinity. So, any questions about this? It's just that because every element of this set right here converges to an element in this set right here, you have the convergence in this Hausdorff metric.
So this would be, again, to borrow that word oracle, it would be if you had so Px infinity as a single measure, is that just a P?
If the state space associated with our experiment is the big omega, yes. If not, Px infinity is an extended probability, and it will induce a regular probability measure, as I show in the slide.
I see. When it's not the same, do you mean it's smaller or do you mean it's bigger? It's the omega itself is bigger.
If we are in the omega prime case, where the state space is smaller, is a proper subset, we have that Px infinity will give negative probabilities to some elements that are those who belong to the latent space, the perpetual latent space, the latent space that will remain latent forever because we discover that the actual state space is smaller.
Okay.
So this is just to answer Robin's question. Again, remember the two possible scenarios. So the first one, we discovered that omega is we retrieved that omega is the state space associated with an experiment, and in the second, we discovered that the actual sample space is omega prime, that is a proper subset. So in the first case, we have that any Px infinity in calligraphic Px infinity is a regular probability measure, and we have that omega f Px infinity is a regular probability space for every element of this calligraphic Px infinity. If instead we are in scenario 2, so we discovered that the actual sample space associated with our experiment is smaller, we have that Px infinity is an actual extended probability measure, and it has this property right here, right? Because this is in the if omega prime is finite, if it's countable, it's the same thing. It's just for ease that I'm considering the finite first. So this because it has to sum up to 1 because this was the error. Right. So this may seem problematic because PXT converges to a set of extended probability measures, not regular, but we want a set of regular probability measures because then we want to start our regular statistical analysis. So we want to describe the regular probability measure induced by every element in this calligraphic PXT. This is the limiting set, by the way, in the finite case. So we want to find, in particular, a p tilde such that p tilde of A is equal to C times PXT of A for every A that belongs to the actual space that is, this is omega prime, right? In the case that is finite. And why would we want to have something like this? We want to have something like this because because we would have that the ratios between extended probabilities are preserved. So we have something that like this happening. And finding such a C is not very difficult, right? It's just a renormalization by the extended probability assigned to the sample space omega prime, which is going to be smaller than 1, but then it will bring us everything to 1. So it's going to define that regular probability measure. And so this p tilde that we can write like C times PXT is the regular probability measure induced by the limiting extended probability, and preserves the ratios between the extended probabilities of the elements of the sample space associated with that experiment. So this omega t plus ft plus p tilde is a regular probability space for every p tilde in calligraphic p tilde, where this latter is the set of regular probabilities induced by the limiting set of extended probabilities given by our analysis. And if omega prime is countable, we proceed in a similar way. Yes, so yes.
So the C
Yes.
technically has a T index, a subscript big T, then it changes as T grows.
But yes, so in the finite case, this corresponds to Px infinity. Can you remember when they said like after T, in the finite case, after a capital T, everything stays the same. So this has actually infinity. And in the countable case, you're right. Here you should have Px infinity of omega prime.
And so if you choose a big T to be a finite time,
Right.
then the C is a function of that. Right? If the C presumably becomes closer and closer to 1, because this P
It becomes closer to 1 if the sample space associated with our experiment is the whole omega, the bigger one. If instead it's a subset, then
okay, so that goes to a positive constant.
yes. Okay.
And may I
Yes.
check, is the reasoning behind preserving the ratio of probabilities that you want to do Bayesian translation?
That's exactly right.
Okay.
All right, so as I promised you, I want to talk about preserving opinions. Right, so in the first scenario, that is when we discover that the sample space associated with our experiment is the whole space of apparently possible states, we have that every element of the limiting set coincides with the corresponding probability measure that we expressed ex-ante on the whole omega. And this should not surprise, right? Because this updating procedure is based on discovering the true composition of the state space associated with our inference procedure. So it's natural to retrieve the opinion we expressed ex-ante on the state space omega once we get the confirmation that the true space is indeed omega. And also, in the second case, albeit not equal, P tilde is proportional to Px infinity. So we maintain our opinion on the elements of the sample space omega prime that is a proper subset of omega, so the one that pertains to our experiment. So again, as I was telling you before, this is a way of coming up. Sorry, of coming up with an initial opinion, in this more general case, with a set of priors, with a set of priors, and instead of giving one right away because we don't know the composition of omega. Right. Any questions? So this is the example that I was telling you about species sampling problem. This is a very, very toy example. It's just to give you an idea of what we had in mind. So suppose we want to know the number of bird species that inhabit a certain region throughout the year. And we start the analysis by letting omega be the whole naturals and omega 0 plus be 1 through n, where n is the number of species that inhabit a region similar to the one we're interested in throughout the year, but not quite the same. So maybe they are closer geographically or closer naturally from an environment point of view, something. And suppose we face ambiguity, so we specify a set of probability measures on n, for example, a collection of geometric distributions. Then we proceed as we did before, and we compute the extended probabilities induced by this. So we flip the probabilities to the events that are not in omega 0 plus, and we keep the positive probabilities of those who live in here. And then we collect observations, say, for a year. And we discover that the state space associated with that experiment is some omega prime is 1 through n, where m is bigger than the n we specified here.
Were all those other species observed?
Yes.
The ones the end you started with?
Yes, these are just assumed. So suppose you are in region 1 of a park, and you have data about region 3.
You don't worry about whether you see them.
No.
You don't worry about whether you might be wrong about them.
No, exactly. So and suppose that after a year we end up discovering that the state space is some omega prime that goes from 1 through m, and m is some number bigger than n. Right, and so we obtain the set calligraphic P tilde of regular probabilities induced by Px infinity, and now the real statistical analysis can take place. So n here is the maximum number of species that live in the region during the year, but it doesn't take into account migrations to or from the region or any other phenomenon of this kind. So the number of species may well be smaller than n. So what we do, for example, if we want to use Bayesian conditioning, we gather data y1, yn, and we condition, we compute the Bayesian update of every element in this set right here. And for all omega k in omega prime, where omega k are just the numbers, so 1 through m, the posterior probability of omega k being the correct number of species belong to the interval given by the lower and upper probability associated with this set. And of course, the narrower this interval, the less imprecise our beliefs resulting from the analysis. Okay, so this was one of the motivating examples that drove us. Now, a criticism that we came up ourselves was, why should the scholar be concerned with the exact composition of the state space, right? So it may be enough to specify it as richly as possible and then proceed at a regular statistical analysis. So we have two responses for that. So the first one is that the scholar would not be respecting the condition in Cyclis that the state space must have the right granularity depending on the statistical experiment at hand. And then if the state space associated with our experiment is a smaller set omega prime, working with probability measures on a much bigger set may be computationally costly. So our ex-ante analysis allows the scholar to focus on the minimal state space, that is those containing only the necessary states.
Do you want to explain granularity?
Yes, so here again, I think what he had in mind was that you don't want a state space that is too granular, so too rich, if you could perform a successful analysis with something less rich, something more coarse. Does that make sense?
I don't. Where's the coarseness?
Yeah. So, for example, think about.
Is this problem is something more or less coarse?
Yeah, no. I think okay. So think of a soccer match, right? He's saying if you can get away with just considering omega being a useful result and a loss, useful result being win or draw, you don't need to have win, draw, and loss.
Okay,
so
I understand that concept of granular.
So you don't want something that is too granular.
So why is okay, maybe I understand. Sorry.
No, I'm more than happy. Yes.
Sorry, can I ask, you can also defer this to later Q&A.
Sure.
But because you're defining the extended probability over the entire omega,
Yes.
why are you thinking, I was not quite seeing how you're addressing motivated by the granularity concern, because the idea would be like starting with a smaller space and then you add in possibilities, but actually
we are doing the other way around. We start from the most granularity possible, and if we end up discovering that the one we need is less rich, we're going to use that one. So we don't need to work on the very big dimensional one that can be costly from a computational perspective, say, but we can focus on the smaller one once we discover that that's the one associated with our experiment is a smaller dimension.
So your perspective is actually compatible with the specified as rich as possible. It's just you don't want to work with the
Yes.
That's as rich as
Yes.
possible.
So granularity would normally mean that how much you subdivide it.
Yeah. No, here again, it's very realistic. So in the future, what I would like to do is to be able to deal with an ex-ante analysis that does not discover the whole state space, but only a subset of it, even though the whole state space may be bigger than that. And we would also want to relax the assumption of working with finite or countable state spaces. We would want to have omega being possibly uncountable. And also, for those of you who are interested in quantum mechanics, we would want to better reconcile this interpretation of ours with the possibility that people who work in quantum mechanics give to probabilities that go over one, above one, instead of just stopping at one. So that is something that we really want. So thank you for your attention, and if you have any questions, I'm more than happy to. Oh, by the way, I have other material. In particular, I have some more things about upper and lower extended probabilities, but it would have been too much, and also some more properties of generic properties of extended probabilities, but those are more just technical. They don't add much about the discussion. So.
Thank you.
Thank you.
Thank you.